Okay, let's get started. We are working our way through the third technology we will be talking about in our section on looking outward. We started by talking about traditional desktops, laptops, and cell phones. Then we moved on to embedded devices, which have sensors which can directly sense the world. And now we're talking about robots, which are basically moving embedded sensors, so they can actually act in the world and sense the repercussions of their actions. The reason why we're talking about robotics in an HCI class is because the nature of the interaction with a machine with its environment is very different than a computer which is interacting over cyberspace. And also, as robots begin to appear in our everyday lives, there are unique kinds of interactions that we might engage in with robots that are different from how we typically engage with computers and so on. So I think probably on Wednesday we will get not to HCI but HRI and look at some of those differences. What's going to be different when you're interacting with the technology that itself can interact with the physical world in ways similar to the ways you can. Okay, so back to lecture 20. We finished lecture 20 last time. We ended with this in-class exercise. So in your ASL educational software, you've turned it into a stateful program. So the program is running an infinite while loop, and on every pass through the while loop, it's detecting which particular state it's in. And depending on what state the code is in, it will create a particular interaction with the user. The hypothetical robot swarm that we were making last time is not dissimilar from that. So in this case, if you have a look at the pseudocode we have here, imagine that each robot in our swarm has some Python code that's running. Each robot has its own infinite loop that is running. And every time it passes through that infinite loop, there's a set of if-then-else statements. So it's detecting that robot is detecting what state it's in. And state, in the case of a robot, is dependent on certain sensory situations. So there are two different states we can think about, whether the robot is holding an object or not, right? It's up to you in this in-class exercise how many of these states you want to define, but the states are defined by sensory information. Then the question is, once the robot detects that it's in a given state, like holding an object, the robot is going to change its interaction, and in this case not with the user, but with the physical environment. And the robot is going to change the way it interacts with the environment by invoking a different Bratenberg vehicle. So in this case, we have when the touch sensor is firing, the left heat sensor is attached to the right motor, and the right heat sensor is attached to the left motor. So as long as the robot is holding an object, what behavior is the robot exhibiting? What's the robot doing whenever it's holding an object, according to this Bratenberg vehicle?
Moving toward the hotspot.
Moving towards the hotspot, right? Which is good, which is kind of what we want it to do, right? It's supposed to be bringing objects in towards this central location, which in this case is a heat source. Okay, that's not going to be enough, though, for the robots to move all of these objects with lights on them to this central heat source. What other states and other behaviors is the robot going to have to exhibit in order to clean up this site?
They need to avoid each other. So
They need to avoid each other, right? These are very expensive machines. How are we going to get the robots to avoid each other?
The machines also have a sound sensor.
Yep.
They can emit a sound, and if a robot is within range of another one, and the decibels go over a certain limit,
Yes.
then they can direct each other away from that sound without
Okay.
as
So
far as I know.
okay. So we're starting from one of the functionalities in the requirements here. The robot should avoid one another. We've identified the sensors which are going to be relevant here, which are the sound sensors, right? Because again, as good HCI designers, you're already thinking about invisible text that's not in the requirements, right? The robots either emit sound just because they're moving around, or maybe we need to put some sound on them. They need to emit a sound. We're thinking about the physical context of these robots moving around on a construction site or on the surface of the moon. It doesn't really matter, right? We're starting to think about what else is going on in the physical environment of these robots that actually makes it easier for us to program them, right? We could put video cameras on top of all the robots and have them scan for each other and detect other robots and move away from them. But as Breitenberg taught us, if we think carefully about the environment, which is there's other robots around that are making noise, all I need to do is to detect whether the decibels go above a certain level, which is going to be a new state, robot nearby, and what should the robot do when it's in that state?
Can the robots still hear each other if there's like a storm on Mars?
Good question, right? So what other ambient sounds might be out there, right? If there's a storm, or maybe the ground is hilly, so there's something in the way. Maybe these objects themselves are emitting noise, right? We don't know, so we might have to go back to NASA or the stakeholders and elicit additional requirements from them. Remember our discussion a few weeks back about the HCI design process, right? Doing a lot of user testing, trying to elicit the right set of requirements. Let's assume for the moment that the only real sound sources in this environment are the robots themselves. What do we do? What should a robot do when it detects sound above a certain level? We're going to have to instantiate not this, we're going to have to swap out this Breitenberg vehicle, and it's going to have to do something else in response to sensors. What is it? How should the robot react to sound?
If it's on like the right, it should slow the left wheel.
If there's, right, so if both sensors or one of the sensors goes above a decibel level, then if there's a lot of sound on the right, the left wheel should turn slower, right? And if there is more sound on the left, the right wheel should turn slower, right? So crossed connections, that was the contralateral connections with positive or negatives on the wires.
I mean, you could do either. You just have to switch which wire they're crossed. I mean, if you have like the positive on the right, and then microphone here's from the right, it would still turn the proper direction. It's just, you know.
There's more than one way to do this. So we've got our two sound sensors up here. We're thinking about using the crossed connections. So if there's more sound on this side, this wheel should turn slower so it turns away from the loud sound. So are these plus or negative connections?
In that case, they'd have to be negative.
They're negative, right? So these are inhibitory connections. The more the sound sensor fires, the more it inhibits the motor, which in this case means that the wheel will spin slower, right? So there we've added a new if clause or a case statement to our switch statement here, that if there is sound, we turn away from it, and that should cause the robots to avoid one another. But it raises an additional challenge, initial problem, if you think carefully, again, about the physical context here. We want the robots to bring all the lighted objects towards the heat source, and we want them to avoid loud sounds.
So they're all going to head towards the same place and avoid each other.
Exactly, right? So we know where they're going to start to cluster. They're going to start to cluster around the heat source because they're going to be bringing things there, which means it's going to be pretty loud nearby. And so some of the robots that are bringing objects in might veer away from that situation, turn away, then volume drops. Is this actually a problem? What will start to happen? Let's imagine we just have these two states. So this state, and look for light if you're not holding an object, right? So we've got three states basically which correspond to find objects, bring objects towards the heat source, and avoid each other. What will start to happen? What will start to happen near the heat source? They're obviously not all going to arrive at the same time because they'll veer away. It's too loud.
There's going to be more and more light at the heat source.
There's going to be more and more light at the heat source, that's right, which actually raises another problem, because if you don't have an object and you're looking for light, you're going to start to go to the heat source, which isn't necessarily what we want you to do. But think about all the robots near the center that are holding objects and trying to veer towards the heat source and then veering away from the center when it gets too loud. What's going to happen near the center there?
I mean, if they all are taking the same amount of time to get there, no one's going to get there. It's just they're going to like veer off and come back. But if they're taking different amounts of time, they'll be like staggered.
It'll be staggered, right? So obviously in the worst case scenario, if they all come in at the same time, it gets really loud, they all leave, volume drops, this situation kicks in again, which means now they're interested in heat, they turn around and go back to the heat, they all arrive at the same time. You get into this vicious cycle, which you don't want. But again, thinking about the physical situation here, that's probably unlikely to happen, right? Some are going to arrive slightly before others, so they might sort of move around seemingly randomly in the periphery of the heat source, and when it's relatively quiet, one of them will kind of get in there and drop off its cargo and then turn and move away. The others will stay away because it's kind of loud at the center, and another one will go in and another one will go in. Most likely it will sort itself out, not unlike the situation with ants that lay pheromones, right? Again, thinking carefully about this problem, we can get away with relatively simple robots in this case. We don't need to add in additional code to say what the robot should do if there's a traffic jam at the center. If we get this right, they should sort of sort this all out on their own collectively. Okay, I think we'll leave this example here, but hopefully I've impressed upon you the message that Breitenberg was trying to make, which is, like HCI designers, roboticists have to think very carefully about the physical environment that the robots are going to be placed in. And if you do, it's not necessarily that the complex physical environment in which these robots are going to operate is an obstacle. It actually provides opportunities, right? We can get away with creating relatively simple machines that exploit rather than fight against the complexity in their environment. Okay. So that's lecture 20. We're going to switch now in lecture 21 to talking about a philosophical question, which is situated and embodied cognition. The reading for today comes from How the Body Shapes the Way We Think, HTB chapter 4. This is from a book I co-authored a few years ago. In this chapter, there's a fair bit of material that's not relevant to what we're going to talk about today, but I'll highlight what aspects of chapter 4 are relevant for us today. We're going to talk about these two ideas of situated cognition and embodied cognition because they really help drive home the difference between robots, this particular class of technology, and other technologies that you may already be familiar with. Okay, so here we go. Let's start with looking at people. People are situated in the world, and they possess a body, right? They have a body with which to push against the world and observe how the world pushes back. Situated means, again, they're situated in the world in the sense that they're directly sensing the world. Once you have someone or something that is both situated and embodied, you have these particular kinds of feedback loops. So here are two embodied agents, in this case, two humans. One human is outputting sound, they're talking, which is immediately picked up by somebody who's nearby who hears it. This person then listens and says something back, and you get this particular feedback loop. Unless person one plugs their ears, they can't help hearing what person N is saying, right? It's immediate. That is very different from computers, which are neither embodied nor situated. So a computer might output a packet, and it might travel across a wire. Computer one may then collect that packet at its leisure, right? There isn't this immediacy or this real-time feedback that exists in the physical world. Okay, so this cartoon here, this is an attempt to try and show you that, yes, computers exist in a particular world. It's called the internet. But the digital world is very different from the physical world. The physical world admits different kinds of feedback loops, right? As long as you're standing near someone, their output immediately becomes your input. What you do with that input is up to you, but it's immediate, right? We obviously use technologies to communicate with others and slow things down through the internet. But in a physical setting, there are particular aspects of this feedback loop that we can't avoid. Okay, let's start with the sort of easier one here, which is embodied cognition. So here's an old Dell desktop. Yes, it is a physical object, but it doesn't count as a body because a desktop cannot use its case to physically influence the world, right? Maybe it can emit some heat, but that's kind of about it, right? That's very different from our little Lego robot over here that can move around and immediately sense the repercussions of that action. Okay, so the way you process information, embodied cognition is an approach to thinking about thinking, which says cognition is not just about what's going on inside your skull. Important aspects of cognition have to do with the fact that the brain sits inside this machine that it can operate in the physical world, right? The moment you start thinking about that, your thinking about thinking changes. You have to be able to deal with things in real time, right? If you have a body that can move and you can see, your moving will cause immediate feedback. Non-embodied technologies like computers don't necessarily must wait for feedback from other computers and other non-embodied systems. Now let's talk about situated cognition. So situated cognition is, again, this idea that cognition is influenced not just by the fact that you have a body with which you can push against the world, but that you have sensors and you can observe the repercussions of that action. Right? The way you process information is affected by the fact that you're physically situated in the world. You're sensing the world in real time. So an embedded device is situated but non-embodied. Right? So the intelligent light sensors in the data center, they're detecting movement or noise, and that's just happening. Right? They can't move or affect the world. They are minimally embodied in the sense that they can have a little bit of an influence on the physical world, which is what? So the intelligent light sensors in the data center, which turn on and off the lights depending on what they sense going on in the room, why are they minimally embodied? They don't have bodies like us or robots where they can move around and impact the world, but they can impact the world a little bit. How so?
They're providing data to another system that then physically affects the world.
They're providing data to another system which then affects the world, which is turning on and off the lights, right? So we're starting by sort of thinking about embodiment as a black and white thing, but of course it's not, right? Devices can influence the physical world. It's just a question of how directly they can do so. Okay. If we consider a human, an animal, or a piece of technology that is both embodied and situated, we typically refer to this as a complete agent. It's complete in the sense that it can push against the world and observe how the world pushes back. The reading for today talks about 5 properties of these kinds of agents. So if you are an agent that's both embodied and situated, there are 5 aspects to your existence that you can't avoid. We're going to ignore number 4 and 5, which you'll find in the reading today. We're going to only focus on the first 3, which are relevant for HCI. The first one is kind of the most obvious one. The moment you are a physical object existing in the world, you are subject to the laws of physics. A computer is also obviously subject to the laws of physics, but in a sort of trivial sense, right? If I'm an object, if I'm a complete agent and I have a body and I need to move around in the world, then things like mass and momentum and inertia and friction matter to me. They're going to act on me no matter what I do, right? I can't avoid that situation. I'm subject to the laws of physics. The moment I move as a complete agent, I generate sensory stimulation through my behavior. And through my behavior, I also affect the environment. I may or may not have the sensory capabilities to sense how I've affected the environment, but I definitely do, right? The moment I move around and knock into things in the world, I'm affecting the environment just because I have a body. Okay, why does that matter? If we think about designing robots or designing technologies that are interacting with people out here in the real world, we want to try and think about these three properties and write code for them which exploits those properties rather than tries to fight against it, right? Again, not unlike we saw in the case of Bratenberg's vehicles. So you're creating some technology that someone is wearing or someone is interacting with out in the world. How do we exploit these three properties? Well, let's look at a few examples. Let's start with a complete agent, and we're going to think carefully about how it's affected by the laws of physics. Let's imagine that we are tasked with designing a device that can record various environmental information at different levels of the atmosphere of Saturn's moon Titan. There's different ways we could do this. We also want to try and collect photographs and images from the ground. So we're working for NASA here to develop a solution to get this information for them. One solution would be to put a satellite in orbit around Titan and do some very, very fancy things with radar and other sensors that are able to ping to certain levels of the atmosphere and sense the return signal. We could do that. We're now talking about a very, very sophisticated device. Or we could do the alternative, which is exactly what NASA did in 2005, I think.
Send a robot?
Send a robot, which does what?
It like wanders around in the ground.
In this case, there are two that do on Mars. On Titan, the device that they sent did not walk around. The most important thing that the Huygens probe did was what? It was subject to the laws of physics. Which law here matters?
Is this the one that crashed into it?
Yep, that's right. It just fell and landed and lasted a few minutes, long enough to take this picture, right? You deploy the Huygens probe, it's going to fall, right? It's going to be acted on by gravity. And as long as the probe can sort of sense its altitude, it does different things. It takes pictures with different kinds of cameras and sensors, depending on how high it is. And it slowed itself enough that it didn't destroy itself on landing and managed to snap a few pictures, right? This is kind of a cooked example, right? But again, we're relying on something that's pretty simple here. Here's a device that's acted on by gravity in this case. We want to collect information from different levels of the atmosphere. Instead of staying above the atmosphere and writing millions of lines of code to do very fancy things with radar and other passive sensors, let it fall and do what you can to make sure it survives when it hits. Even in the case of Huygens, even if it didn't survive, we would have gotten this back, which is immensely useful already. Kelly, did you have a question?
Didn't we do the same thing with a comet recently?
Yes, exactly. NASA loves this, right? This works perfectly fine. Let it crash on the surface, right? If it happens to survive, even better. We can collect a vast amount of information just because, even in the case of the comet, which had microgravity, there's enough to pull in the device.
So is it just because like they can't keep like a constant orbit by using some sort of like boosters for the telemetry? Or?
Well, they could. It's just exceedingly complicated, right? If you want to keep a constant height above a planetary body or a comet, it's tricky, right? You could do it. It depends on what your goal is. If you want to collect telemetry at different levels of the atmosphere or at certain altitudes above the comet, think about the fact that this thing will be pulled in by gravity, assuming the object has enough gravity to do so, right? Makes things pretty simple. Okay. Here's a situation that's a little bit closer to Earth. Hopefully you all recognized who this was in a fraction of a second. If you didn't, there's the answer up here. We're going to now think about a computer vision problem, which is known as image segmentation. So I give you the photograph in the top left here, and even before I ask you who this is, I just ask you to separate foreground from background, which again, computers are getting pretty good at these days. But this was a really difficult problem in computer vision for 40 years. We're going to look at two different ways of solving this problem. The first one is the non-embodied case, which is we just feed in this image, or we feed in millions of images of Marilyn Monroe and a million other images that do not contain Marilyn Monroe. And with a very sophisticated machine learning algorithm, KNN is not going to cut it here. With a very sophisticated machine learning algorithm and some very, very fast computers, a computer can now do this, but it's a very, very complicated problem to solve. It's exceedingly complex. Why? If I were to march along this image and visit each pixel and ask you whether it's background or foreground, you'd be able to do it pretty well. But it is a complicated problem. Why is it complicated?
Because the computer will just see a bunch of color and transparency values and not know what goes in what, or what part of the photo is good or anything.
Absolutely, right? So we're kind of tying a computer's arms, both arms behind its back, pun intended, right? It has no body. It has an impoverished view on the world, right? All it has is colored pixels, which is all you have right now. And again, you probably did it pretty well. But the question remains, and this is unknown in developmental psychology, which is how you learn to do so, right? Hopefully your parents didn't tie both your hands behind your back and expose you to millions of photographs with and without people in them until you were able to recognize people, right? So the theory goes in embodied cognition that we used our bodies growing up to learn about the world around us. And by doing so, we gradually scaffolded off of physically manipulating objects to gradually removing the scaffold so that we could recognize objects without having to physically interact with them. That's the theory. Even so, assuming that we do make a machine that can interact with objects to recognize them, how would the machine do that? I'm going to show you a machine that does do that, and it does it by relying on these two other aspects of a complete agent, which is when I act, I generate sensory stimulation, and when I act, I affect objects in my environment. Okay. So let me introduce you to BabyBot. Here's a cartoon picture of BabyBot up here. This was work done at MIT and Italy. And BabyBot was tasked with exactly the same problem, which in this case was not to recognize Marilyn Monroe, but to segment foreground from background. So BabyBot was put in front of a table, and on this table they would place a number of objects, and BabyBot had to learn to separate the objects from background, which in this case is the surface of the table. Unlike our non-embodied machine learner, BabyBot does have, well, not two arms, but one arm with which it can interact with the objects on the table. As you can see here, BabyBot also has two eyes, so two cameras. However, these cameras are downsampled, meaning a lot of the information is thrown away. For each pixel in the image returned by the video camera, each pixel in the video stream is binarized, black or white. Here it's actually grayed out or not grayed out. A pixel becomes white if for that pixel there was no movement detected at that pixel in the last millisecond. And that pixel was painted black if there was motion detected at that position in the last millisecond. So in essence, they're scraping most of the information out of the video stream and just leaving in where the robot detects motion. Okay, So let's walk through a use case with BabyBot, which is an example interaction of BabyBot, in this case with the world. BabyBot starts with its arm out here, and it's looking down at the table with these objects on the front of it. What do you think BabyBot sees in its video stream?
Just its arm moving?
It doesn't see its arm moving, hasn't even started moving yet. Its arm is out here. It sees nothing. It sees all white pixels because, as far as we can tell from what I've told you so far, there's nothing moving in BabyBot's field of view, right? BabyBot now sends some current to its arm, and its arm swings into its field of view. What does BabyBot now see?
Sort of a silhouette of its arm.
It sees a silhouette of its arm, right? There's this blob of black pixels. BabyBot doesn't know arm. All it knows is black and white, and it knows whether it's sending electricity to its arm or not. So it says, I sent electricity to my arm. Suddenly I saw this big black blob, and it's a silhouette. If it stops sending electricity to the arm, what happens?
That silhouette disappears.
Silhouette disappears, right? It sends commands, the blob reappears. It stops, the blob disappears. It sends commands. What is BabyBot already learning even before it's touched any of the objects on the table? Or what could BabyBot start to learn from this interaction with its physical environment?
Proprioception, I guess?
Proprioception, right? So it's starting to learn something about the angles in its arm. So proprioception is measuring angles in the arm. But what more fundamental lesson is BabyBot able to learn here?
Unless something is moving, it won't be able to detect.
Unless something is moving, it doesn't know about something yet, right? All it knows is black silhouette and electricity, yes or no, to my arm. Doesn't know thing because there are no things yet.
Well, knows that it controls that blob.
It knows that it controls that blob, right? So contingency, meaning if I do this, this happens, right? If I move, I generate sensory stimulation. So whatever this blob is, it's me. For the moment, that's all I know. There is me and a field of infinite white out there, right? So at this point, BabyBot is a solipsist, right? I exist, nothing else in the universe exists except me. It remains a solipsist for all of about 3 seconds. As it keeps moving, suddenly the blob changes shape. Now what happens? It's moving, seeing this particular silhouette, and suddenly the shape of the silhouette changed.
It's encountered something.
It's encountered something, right? So BabyBot says, there's things, there's something else other than me, and I'm just for the moment going to call it thing. I don't know anything else. It's just a thing. What does it know about this thing?
You can figure out its shape.
Figures out its shape, right? So unlike our complex machine learner back here, which has to carefully try and trace out the shape of something, because BabyBot is situated and embodied, it gets shape for free, right? Whatever this thing is, it has this shape. What else can it start to learn about this thing in the next few seconds?
But it's not part of it.
It's not part of it. How does BabyBot know that thing is not me?
Because it's like motion isn't entirely based upon electricity.
Right. Remember we talked about correlation in the last few classes, right? This particular blob here, its existence correlates perfectly in time with whether or not I'm sending electricity to my arm. This thing doesn't. It didn't exist while I was sending electricity to my motors, and then suddenly it did. What happens if BabyBot stops sending electricity to its arm? What happens in the next few instants of time?
The apple would stop moving and cease to exist again.
Does the apple stop moving? Maybe. Depends, right? Depends on what? Possibly. BabyBot's doing this, comes in contact with the apple, stops sending electricity. What happens to the apple? It may stop moving, in which case it disappears.
Well, the apple just rocks back and forth.
Maybe the apple rocks back and forth, right? So BabyBot stops moving, me disappears, but this other thing that I'm calling thing is still there for half a second, and then it disappears again. That's interesting. So there's these two things now. There's me and thing is different from me, just in the sense that it has a different shape, and it's not contingent on my action. Sometimes it moves when I'm not moving, and sometimes it doesn't move when I am moving, right? So already we have a kind of segmentation here, not between foreground and background, but between me and everything else. So BabyBot is no longer a solipsist. It knows that there are other things out there. Now it starts to move around at random. It says, well, if there's one thing out there, maybe there are other things out there. And now it starts to hit, let's say it comes into contact with a bundle of grapes. What happens in this case? What's different? What will be different when BabyBot comes into contact with the grapes than when it came into contact with the apple?
There's a lot more moving parts.
There's a lot more moving parts, right? So there's this, I come into contact with another thing, I'm going to call it another thing. It has a different shape already from the get-go, but then something else starts happening, right? The shape itself starts to change over time. Up to this point, BabyBot has not seen that situation, right? Everything it's seen so far, these two things, me and thing, always have the same shape. But now there's something that changes shape. So BabyBot says, okay, it turns out there are not just objects out there, but there are classes out there to which objects belong. And I'm going to make up two classes, one called hard and one called soft. The first two things I've ever experienced in my life, those go in the hard basket, and this third thing I've discovered goes into the soft basket. So we're already starting to make progress on understanding the world around us. Okay, let's,
I was
yes?
just curious, does BabyBot have some sort of like pressure sensors for touch or anything?
It does, but in this example here, you don't even need it, right? Of course, if touch is turned on, it could start to learn lots more. Given what I've just told you, and thinking about what BabyBot can exploit, BabyBot can do things. It can push against the world and observe how the world pushes back. And some of what it sees is its effect on the environment, in this case, the objects in front of it. What else could BabyBot start to learn about these objects in front of it? So it knows there's a thing called me and things that aren't me. Those things have different shape.
If it knew the size of its arm, it can figure out the size of the other objects by comparing them.
Okay, yeah, so maybe it says, okay, it looks like if I just count up the total number of black pixels, there's this other property that objects seem to have, and I'm going to call that size. Right? Okay, things have different size. There are some things that are smaller than me. There are some things that are bigger than me. If it starts to come into contact with smaller and bigger objects, what else is it going to start to learn about size that matters?
If it like pushes a big object, it'll move the smaller one. If it pushes the smaller one, it might not move the big one.
More contingencies will start to appear, right? It's going to learn that things that are big either don't move or take much more electricity to get moving, and generally speaking, smaller things require less effort. So there are these two properties, which I'm going to call inertia, and this thing inertia seems to be related to this thing called size. It doesn't know about mass yet, but it does know about size. What else could BabyBot start to learn about these objects?
I guess how shape would affect movement.
How shape affects movement. So BabyBot is named BabyBot for a reason. It's supposed to act like a baby. What else do babies do? They do a lot of this. What else do they do to try and learn about their environments?
They put things in their mouth.
They put things in their mouths, right? I think I mentioned this before. The moment you put something in your mouth and you try and bite on it, you learn, first of all, whether it tastes bad or not. That's pretty important. Whether you can bite into it or not, whether it's breakable, whether it's separable. You can learn about texture, size, malleability. Huge amount of information that you can get out of biting into something. I don't know if we would want BabyBot to do that, but we might give it other sensors that allow it to easily determine these properties. Maybe BabyBot does this and learns that certain objects are mashable and others aren't, right? Can it break things or not? It's a pretty important thing we want a robot to learn, especially if they're going to be humans interacting with this robot. We want BabyBot to know that we're much more like grapes than we are like metal objects, right? Okay, so again, you don't need to remember all the details of BabyBot. The main thing is that BabyBot is able to learn a lot about its world by physically interacting with it. And this is not just an academic exercise, right? We're on the brink of deploying autonomous cars on the road, and autonomous cars know something about road environments, which they have learned by being supplied with huge amounts of sensor data about roads. And this is an important philosophical question, but also a very real and practical question, which is going to spell the difference between whether autonomous cars are legalized on our roads or not. Is that a sufficient understanding for an autonomous car to operate safely compared to this? Do autonomous cars need to physically interact with their environment to really learn about them? And what kinds of interactions are necessary? Is it enough for autonomous cars to sort of learn at a bit of a distance by just collecting information from their passive sensors or their sensors from a distance? It's an open question for debate. Okay, let's move on. So we've talked a little bit about situated cognition and embodied cognition. Complete agents have both. And again, this becomes kind of philosophical, but if cognition does not end at the surface of your skull, cognition importantly contains what you do with the environment. What happens if you're a social agent? You're interacting with other robots or other humans in your environment. A lot of people have made the case that cognition is then really distributed, right? I need to know if I do this and my friend hears me say that, what do I think my friend will do in response, right? So cognition is not something that's locked up in the brain case. It's something that we can only define, if we want to try and define cognition, by taking into account not just the fact that the agent that's doing the cogitating can push and sense the repercussions, but it knows that there are others that are doing the same thing, right? This takes us also into social cognition. I know that if he said that she would probably do that in return, and that he would react unfavorably to what she did in the following manner, right? As children, we start to learn about that after we've started to figure out about these kinds of things. There are other things out there that push back. Okay. We've talked about affordances already. Affordances are a big part of this, right? We spent a lot of time talking before about how we look around our environment, and we're not just looking at the geometry of an object, but we're doing something very important, which is thinking about how we might interact with that object. And it's really our thinking about how we would interact with that object, which defines what we think that object is, right? So a door handle is a door handle as long as it affords the ability to open and pass through a door, right? And some of us get that wrong sometimes. Okay. So obviously these kinds of things are going to matter when we're talking about technologies that exist out here in the physical world. But of course, we're on the brink of large-scale virtual reality and augmented reality, where we're bringing virtual and physical worlds together. This is a quaint and dated virtual reality system now, Second Life. Does anybody know if Second Life even still exists?
Pretty sure it's near dead.
It's near dead. Okay. So we'll just use it as an example today, right? As we start to build other virtual reality systems, typically you have an avatar in that virtual environment, and that avatar, which is a virtual extension of you, is embodied and situated in its environment. Your avatar can push against the virtual world and observe how the world pushes back. So in virtual worlds, or how do video games or other virtual reality systems, how do they advertise affordances in those virtual worlds?
The same way they would in reality.
The same way we would in reality, right? So if you want a bunch of people to sit together in a certain place, put a table and put a bunch of chairs around it in that virtual world. So obviously we can exploit the affordances we project onto physical objects by making virtual analogs of them in the virtual world. But virtual environments and augmented reality afford us abilities to go above and beyond what we can do in the physical world. How else might you advertise affordances in virtual environments?
I mean, like, a really common one I see in, like, games like Half-Life or whatever, you go up to, like, a door that you can open, a little thing will appear that says, like, E or whatever the button is, the keyboard button you press to open the door.
Okay, so we could do what I told you not to do in the ASL thing, is say, this is something that you can interact with in the following ways by pressing this key, right? And again, yes, of course, we could do that. But as our virtual worlds become more and more rich, we would prefer not to sort of paint everything with text. But given what we've talked about in terms of visual representations, how might we do it?
This is, I guess, side note.
Okay, that's fine.
Affordances in the virtual reality, we have to be very complex, because what if we don't have an animation or the ability in the game to sit?
Absolutely.
But we have a chair.
Exactly. So if you create the next virtual reality system and I try it out, and I see my avatar in the world, and I see a chair, and I try and get my avatar to sit in the chair, but unbeknownst to me, I can't get the avatar to sit in the chair, you have helped me form the wrong mental model about what's possible in this system, right? The moment you put a chair into this world, you're already influencing how your user is going to build up a mental model of what's possible and what's not in this virtual world. That's exactly the point, right?
One thing that is also kind of a side note is, like, there's a lot of people will try, like, especially if the game is really popular, will try to, like, just figure out what is actually possible. So, like, for example, if there's, like, a certain area you can get in, some people will try and get out of that area and see, like, weird glitchy things.
Absolutely. Right, we talked about navigating in information spaces, right? What is the first thing that people do in novel environments? For good reason, try and find all the exits, right? Or map out what is the boundary? How can I get out of here? What are all the ways that I can break things in this situation, right? Abuse as well as use.
In a lot of older games, they used to do some sort of like color gradient so that you could see an object, and like a chair you can interact with might be a little bit lighter color than a chair that you couldn't.
Absolutely, right? So maybe we lighten certain objects, or they're slightly more opaque and everything else is a little bit translucent. All those little subtle cues, which for most people they interpret in the right way. Let's imagine I come up to a door and I'm trying to get my avatar to open it. The avatar has a hand, and the hand is trying to reach for a non-existent knob. What might I want to see the door doing to know that I'm going down the wrong path? Whatever, I've clearly interpreted the affordance wrong. This door is not meant to be opened, or it's a picture of a door, who knows what. But I can't open it. How would you signal that to your users?
Show a lock on it.
Show a lock on it? What are you doing in your own ASL system at the moment?
Thumbs down.
Thumbs down, maybe. Maybe the door gets increasingly red, right? Whatever I'm trying to do, it's not working and it's getting worse, right? Go do something else. Or I don't know what this object is and I'm manipulating it. I'm doing exactly what BabyBot does. And the object's getting slightly greener as I do it, right? Subtle hints that I'm on the right track for building a mental model of this system by interacting with it, or subtle hints that I'm on the wrong track and I should do something else. We could put up a whole bunch of notifications and error messages and all the rest, but we want to not try and distract the user too much from what they're doing, right? So what are those subtle cues that we could build into a virtual space to help build up affordances above and beyond what we can do in the physical world, right? That's again an example of trying to exploit the opportunities rather than fight against the natural tendencies of humans, which is to figure out how to interact with mysterious objects in their environments. Okay, I think that's a good place to pause for today. We'll finish this off on Wednesday. You have a quiz due tonight, and weekly report 1 is due Wednesday night. Thank you.